Hi everyone, welcome to lesson 17 of the Advanced Higher Stats course. In this lesson, we'll be learning how to assess the linear association between two variables. You will find this skill on page 31, 32, and 33 of the Advanced Higher course spec. By the end of this lesson, you should be able to calculate R and know what it measures. You should be able to calculate R squared and know what it measures. You should be able to calculate residuals, make a residual plot, and interpret residual plot. Let's start off with R, also known as Pearson's product moment correlation coefficient. R measures the strength of the relationship between two variables, and it can range from -1 to 1. So for example, if you had a strong positive correlation between x and y, R would be, let's say, 0.7 or higher. If you had a strong negative correlation between x and y, R would be less than -0.7. And how you would calculate this is through this equation here, sxy over root of s double x times s double y. And you find this on page 5 of your data booklet. So here are some graphs which show their correlation and then their corresponding R value. You will notice that this isn't the same value I was talking about. This value we call rho. And basically, it's the true value of R. So similarly, x bar is the mean of a sample, and then mu is the actual mean of the population. R is for the sample, and rho is the true R for the whole population. Remember, the R we're calculating is still from a sample, where we have a sample which we made a scatter plot with, and through that we get our S double X, S double Y, SXY, and then we calculate R. It's all coming from a sample, so these aren't the true values. Now let's calculate R. You will find the formula in page 5, and I will not go through calculating S double Y, S double X, SXY, because this is the same data I used for my previous lesson, and I calculated in depth there. So if you want to learn about that, watch the previous lesson before continuing on. And I will just jump straight into this. So S double Y is equal to 526. SXY is equal to -286. And S double X is equal to 159.33. R is equal to SXY, so -286, over the square root of S double X, 159.33, times 526. And that gives us a really low number, actually. It gives us -0.988. Now let's look at R squared, also known as the coefficient of determination. R squared is a measure that represents the proportion of variability in the dependent variable explained by the independent variable. What that means, basically, is how much of an impact does the independent variable have on the dependent variable? And it's measured by squaring R. Very easy. I have some examples here so you guys can better understand R squared. So a high R squared example would be if you were analyzing the relationship between hours of study and exam score. Obviously, if you study more, you'll score better most of the time. There are some students who don't study and get an ace at tests, but there's not many of them. So, because studying has such a huge impact on your exam score, uh, that that makes R squared really high. Whereas if you, instead of comparing that, you compared how people's happiness based on how tall they are, some people, it might have a small effect. Some people might be happy, maybe they're more confident and they're more outgoing because of their height, but it does not have that significant of an impact because a lot of other examples could be their social life, their work life, their health, family relations. All of those things also have an impact on happiness. So because height has a small impact on happiness, r squared is low. Right, now let's calculate r squared. R squared is equal to r squared, yep, shortcut there, which is negative 0.988 squared, which gives us 0.9761. So even with r squared, it shows that in this example, x has quite a significant impact on y. Okay, enough of the r stuff. Now we'll be looking at residual plots. So as a bit of recap, a residual is achieved by take away the predicted y value from the observed y value. This is where y and y bar come into place. Y bar is the predicted value, y is the actual observed plotted value. You can plot these in a graph. So something like this, where 0 is here, and then you'll have marks on how far away or how over or underestimated your predicted values are compared to the observed values. And the residual plots, they're basically used to check the assumption that one, the expected epsilon or residual value is 0, that however times you've overestimated and the amount you've overestimated is similar to the amount you've underestimated, so it equals to 0, and that the variance is constant. Now I'd like all of you to look at these residual plots and see if they're good, if they fit the assumptions. We'll start off from the very right. This is not a constant variance. Something is going on here. There's some pattern here. So this would be crossed out. Same for this one. Same for this one here. There's some sort of pattern, so it will be crossed out. This one as well, there doesn't seem to be much of any pattern, but you can see that the residuals up here are way bigger than the residuals down here. So the expected epsilon will probably not be 0, so this gets crossed out. However, if you look at this residual plot here, that looks that the variance is constant, there's no real pattern, and the spread is good as well. There's no one side being more spread out than the other, so this would be a good fit. Now let's move on to making a residual plot ourselves. I prefer if all of you pause the video and try this yourself and then compare it with my results. Okay, first things first, we find the predicted values for all of the y values. First one being 23.4, then it's 34.2, 14.4, 36 on the dot, 25.2, and 10.8. Now we find our residuals, which are, and it's the normal value, the true value, or the plotted value minus the predicted value. So 26 minus 23.4 is 2.6. This is negative 0.2. This is 0.6. This is 0. This is negative 2.2, and this is negative 0.8. Now let's draw our residual plot. And we have 0 here. We'll start off at 20, then 25, 30, 35, because our x values go from 20 to 34. And we'll go up in ones. So 1 here, 2 here, 3 here. Why does this one keep on disappearing? Okay, there it is. And same way the other way, so negative 1, negative 2, negative 3. Okay, so for our x value of 20, here, it was 0, so it doesn't matter. X value of 21, it was -2, negative 0.2. So our X will be somewhere roughly here, maybe a bit higher up. Our X value of 26 had a residual of -2.2. So that would be somewhere down here. Our X value of 27 has a residual of 2.6, which is up here. Our X value of 3.2 has a residual of 0.6, which is roughly here. I don't know why the 1 keeps on disappearing. And our X value of 34 has a residual of -0.8, which puts it here. So overall, it has a okay spread. The expected epsilon roughly equals 0. The variance, it doesn't look like it's a pattern. Obviously, there aren't a lot of plots, so we can't really see if there is a pattern that well. But overall, the data set doesn't look that bad. That's the end of the lesson. Now you should know how to calculate R and what it means. You should now know how to calculate R squared and what it means. You should be able to calculate residuals, make residual plots, and interpret residual plots.